Good day, everyone. I'm Courage Nito from EQ4, here to present mathematical language from GE Math MW. Right, let's get this started. Right, so uh, pretty much everyone could agree that math and language, or at least the common people, right, that math and language aren't exactly in the same category, considering that math is all about numbers and language is all about obviously words and how words are constructed, right? But what if I told you that if you were to look at it at this perspective, you would understand that language is actually a lot like math, and math is a lot like language, right? So, uh, by doing this, you could have a pretty much a deeper understanding for both fields, considering that um, again you get to appreciate how really how similar these two fields are, right? So to give you an example, right, one of the biggest concepts in math are propositions. Well, it could also be a big thing in English, but essentially what a proposition is it's a declarative sentence that is either true or false, right? If we go back to our declarative sentences, um, it's a sentence that ends with a period and is basically declaring something, right? That thus the declarative sentence. So um, there are different types. In math, there are different types of propositions, right? And they could be connected using connective. So basically, it's an operation that combines two propositions to make a new one, right? So these said new propositions, as a result of combining these said two propositions, are called compound propositions, right? So, what are some examples of propositional connectives? Here, as you can see, there are 5 different symbols that represents a propositional connective. So the one that's the upside down V is basically conjunction, and down the V is symbolizes the disjunction. The circle with the cross is called the exclusive or, and this is an implication. This arrow facing to the right is named implication, and the arrow that's facing both sides is called biconditional. So this essentially means, if you were to convert it into English, it would mean end. And this the if you convert this to English, it would be or, and so is this, but either one of the conjunctions is only true, whereas the implication is obviously because, and no, the implications is basically, well, you'll see, but essentially it connects two prepositions, where one preposition is the uh, the the cause and the effect, and the biconditional means basically both propositions have is codependent with one another, but more on that later. So as you can see, you can convert those into you can convert these propositions into bit operations. So bits are essentially ones and zeros that represent certain informations in computers. In this perspective, one would represent true, while zero would represent false. So, if we were to convert, again, this is pretty much the same thing that I just mentioned a while ago. If you were to convert it to, if you were to convert this is this junction here. This junction, it would represent or, the symbol or, the word or, and would represent this symbol, the conjunction, while XOR would represent the exclusive OR. Right. So later on, I will be showing you how to make a truth table so that you would further understand the concept between the proposition and bit operations, right? So, but more on that later. So, tautology, contradiction, and contingency. So this is another very important information. Tautology is basically when a proposition is true regardless of true values, whereas a compound proposition that is always false is always called a contradiction. And a contingency is neither a tautology or a contradiction, right? So logical equivalence are certain laws. These trees are certain laws that help you navigate through tautology, contradiction, and contingency. And implications, like what I was a while ago, I think this is showing this is what I was trying to talk about a while ago, the cause and effect. So here is a more in-depth or more precise way of saying it. So X is the hypothesis and Y is called the conclusion, right? So if you were to convert this, if you put Y on the left side, whereas the conclusion before the hypothesis, that would be called the converse of that would be called the converse. And if you were to put this sign here, this sign represents not, and not X and not Y. So not Y is the inverse of this, and X, not Y, to not X is called the contraceptive of, again, this particular sign here. I don't know why that's a C. That should be a arrow sign. But anyway, always take note that an implication is logically equivalent to its contraceptive, which is where is it? Here. This is the implication. This is always equivalent to this. Anyway, another concept would be the propositional functions and quantifications. So a propositional function is basically a declarative sentence where you make a certain function for the variable x where it is argument. So this is pretty much given. The arguments to p, for example, if I were to give an example, p is p of x is equivalent to x plus 1. Basically, that would mean that if I ever use p over x, that would always mean x plus 1, right? Moving on, quantifications is basically the method where you convert proportional functions to propositions. So this right here to something like to something like this, right? And there are two kinds. One would be the universal quantification. Basically, it means that it is true for all the values of x in the domain of disclosure, if you are given a domain, of course. And in existential quantification, basically, there's within a domain of the within a range of domain, there lies an x where x is true. So let's say I have 10 things in my domain, and everything else is false but one. Then that makes the whole domain true, because there is one object or thing within the domain that is true, right? So all right. Here is going to be the part where I teach you guys how to make a truth table. So basically, the truth table rather shows us how the relationship between the connective things, the connective propositions are, and how they function. Right. So here's an example. This is an example from a very first seat work here in GE Math. Right. So we start off by having these three values: the P, Q, and R. Right. So usually I just start off by filling out the first value, the values here, the values for P, Q, R, and I'm gonna do that by just putting in the random things. So T, T represents truth, and false. F represents false, right? So give us a minute here. False and true. For the interest of time, I won't be showing everything else, because that would take up too much of our time here. So here, given the values here, we'll be solving for the rest of these, right? So again, the not sign here is basically the opposite of the values of the given variable. In this case, it's Q. So not Q. So the opposite of not Q is F and T. Right? So next would be the this one, the not Q or R. Right? So not Q and R. So the first one should be true, because they're of different signs here, or the different what do you call this, different truth value here. So one is false and one is true. So that's essentially what you have to be looking for when looking at the proposition or, because basically you're looking for two truth values that are completely different from one another. And the same could be said for sorry, you can't say the same for here, because they are both correction. Or means if at least one of these things, one of the truth values means true, then the whole equation is true, or this proposition is true, right? So in this case, there's one true right there, so it should be true. And but here it only has it doesn't have any truth value, therefore it is false. And since here you have two truths, either one, and that means that it is true, right? How about this the end values? So the end values states that both both things have to be either both false or both true, right? Not Q, F, and um, P right there. One of them is very different, so that means it's false. And same with same with this. They're the same things, but here this is true because um well, Q and P here are true, right? And here P XOR of um uh not not Q and P, so this and this. So basically this mean the XOR, the XOR symbol, it's basically the same with OR, but I think this is what I've explained a while ago, where it is true, it is only true if only one of them is true, but they can't be both truths. So meaning not Q and P here is false and P there is true, so this should be true. And okay, so this is the same, but this is false because both of them are true, but only one of them should be true. It is not possible that either of them could be true or both of them could be false. Therefore, this is false. Right. Now to the implication. Basically, the implication states that between the two variables, if this first part right here is true, then the second part should be false, should be true also. And if the first part is false, it should return false as well, right? So sorry, it should return true. So for example, it's not stated here, but this should be false. This should be false, and this should be sorry, this should be true rather. This should be true, and this should be true, and this would also be true, because not P and Q, I didn't make the math yet here, but essentially if you took this would both be this one, the first one here would be true, and this one would be false, which would result to false because it's here, and the P here should be true, so therefore this one should also be true. And here in this last example, this is false, and this is true, and this is false if you followed through with what I have said. The conditional statements basically says that either or, it could be true or false. But that's pretty much it, really. So going back, All right. So that's pretty much it. Thank you for listening. And I'll catch you in the next episode. Goodbye.